All right. Hello, everyone. My name is Vincent Ledvina. Sorry I could not be here live. I will pop in after this recording to help answer any questions that you all might have. But tonight I will be talking about Aurora science, star trails, time lapses, and more. So this is for the Antrim photography workshop on September 10th. I'm recording this on Monday, so I'll be there tomorrow in person in the chat just to sort of follow up on anything that I might have missed here or any questions that you have about all this content. So I'll probably run around 45 minutes, and I should be coming in right after that. So 45 minutes to an hour, and you'll have me for as long as you want following this recording. So let's get started. So a little bit about me before we begin. I'm a PhD student up at the University of Alaska Fairbanks, just entering my second year. I study the Aurora. My field is space physics. I've been interested in space weather since I was literally 4 years old. I saw my first Aurora on Halloween night in 2003. So I grew up in Maplewood, Minnesota, which is a suburb of the Twin Cities, and I saw the lights dancing above my house when I was coming back from trick-or-treating, and that really sort of was a pivotal moment in my life, even though I was only 4 years old. I feel like that really just set in motion this passion for space weather and auroras that has remained centered to, basically everything that I do up to now. So yeah, I'm really into the Aurora. I'm a professional Aurora chaser and photographer up here in Fairbanks. I've seen the Aurora hundreds of times, and I'm studying it now so that I can be a little bit more precise and really kind of get the nitty gritty down with the science. So, understanding the science of the Aurora actually does benefit with Aurora chasing. So I've learned a lot while I've been up here in Fairbanks about how the Auroras work and what data to use and things like that. And I feel like I have a perspective now. I'm still not a PhD, so I still have so much to learn, but I feel like now I'm finally getting that sort of, you're looking down at everything and you really can see the whole picture. I feel like I'm finally getting that view, and I'm happy to share that with you all tonight. So here's what I'll be talking about: some Aurora science, really basic stuff, predicting the lights, Aurora chasing 101, and then into the photography stuff. So obviously you're all photographers, so I want to give you some tips, some more advanced, some more advanced direction that you may have not seen before. I'll also be covering the simple stuff too, but I want to also get into some more advanced concepts like Aurora time lapses and also star trails. And then I will be talking about citizen science, which I'm really passionate about as well. So let's get started. So first of all, what is the Aurora? Well, if you ask anybody, they're going to tell you something different. Really, it's not complicated, right? It's nature's most spectacular light show. It's at its core, it's beautiful, right? A lot of us get caught up in the science and what it actually means, but when you see the Aurora, it is just truly breathtaking. It's captivating, it's mysterious, and it's awe-inspiring. I saw the Aurora when I was 4 years old, and then I saw it again when I was 16, and could really appreciate it more at that older age. And then I saw it sort of in this other pivotal moment in 2022 when I was up here in Alaska helping out with a sounding rocket mission. I was up in Fort Yukon above the Arctic Circle for 3 weeks, and I saw some incredible things. And that really sold me. I was like, wow, the Aurora can be this good. I was just mostly surprised more than anything. And I really think that it's that connection that you can get through the Aurora, which lets you relate to nature in just a really true and special way. So, I mean, that's really what the Aurora is. Forget all the science. It's all second to just the beauty of this phenomenon. But technically, if you want to get, down into the weeds with this, the Aurora is light emissions caused by charged particles from outer space streaming along Earth's magnetic field lines, colliding with gases in the upper atmosphere. And auroras are part of space weather. And just like we have weather on the ground, in the form of clouds, rain, and wind, these types of things, we have weather in space. And the sun is really what's driving all of this space weather. So we have the solar wind, which is really the core of space weather. And, it all starts from the sun. The sun is what gives us warmth and life here on Earth, here on the ground. We feel the warmth of the sun when we go outside. It's why life exists in the first place. We look up at the sun and we just see a glowing yellow or white ball of light in the sky. We don't really think much of it, but really it's this dynamic and constantly changing thing that is, it creates this space weather because it is so dynamic. It's not just, a static ball of gas or plasma. There's eruptions, there's changes in the magnetic field, there's little twists and flares, there's fast gusts of solar wind, there's all these dynamic processes that are creating this sort of it's kind of hard to explain. It's space weather, right? Weather is not the same all the time. That would be climate. But yeah, we have space weather, and really it all centers around the solar wind. So what is a solar wind? Well, if we think about an analogy, and this is sort of my theory, my pedagogy, if you will, with science, is that if we can kind of break it down into analogies which we can understand, it'll really help us better grasp what's actually going on. So just like a hot cup of coffee has steam rising off the top, the sun is similar. It's that hot cup of coffee. It's that coffee inside the cup. It's this hot burning ball of plasma, this constant thermonuclear bomb basically going off millions of times per second. And the atmosphere of the sun kind of fades away into space. It's not just this rigid ball. It's sort of a wispy, tenuous atmosphere as it gets out, as you go off from the sun's surface. If you've ever seen a total solar eclipse and you've seen the atmosphere of the sun, you've seen the corona, which is that white, wispy crown. That's where the name corona comes from. And that corona forms the very beginning of the solar wind. So the solar wind is like this constant stream of particles, like a wind blowing out through all of outer space. And it flows out from the sun through the entire solar system. Carried with it is a magnetic field, which we call the interplanetary magnetic field, or IMF. If you've ever heard of BZ, that BZ is the usually referring to the IMF BZ. So the Z component of the magnetic field, because it is in 3D space. So we're not just dealing with one direction. We have an X direction, we have a Y direction, and we have a Z direction. So normally this wind is calm and gentle, right? The sun usually is pretty well behaved, but sometimes it can become strong and fierce, which is when we get more extreme space weather and more potent space weather. So that solar wind carries tiny charged particles with it. It's not made of dust or little air parcels like we have here on Earth. It's made of particles, and those charged particles carry with them a magnetic field, which again forms the IMF, and which can actually interact with Earth's own magnetic field, which we'll get to in a little bit. So this is just sort of going through the ages of SDO, the Solar Dynamics Observatory, and showing some of the highlights from this mission. So it was launched in 2014, and it's seen the sun now in tons of different ways, and you can actually just see how dynamic the sun's surface is. So what we're seeing here is the sun, but it doesn't look like the sun as you would picture it in your head, right? When you think of the sun, you just think of this, again, this sort of white ball of glowing gas in the sky. But the sun, if you send up a spacecraft into outer space and you put a UV filter on the camera, you can image the sun in a really cool way. So here you're looking at images of the sun, that are in extreme ultraviolet wavelengths. So these are not wavelengths that you can see with your own eye, which is why you don't see images like this from the ground. And also the specific wavelength of light can actually penetrate our atmosphere. So you need to send spacecraft to actually take these images so that you're outside of Earth's atmosphere and you can see this light coming in. So what you're seeing here is plasma sort of being illuminated by magnetic fields. So the sun is obviously huge and massive. There's a lot of gravity on the sun. But as you get further out from the sun's core, the effect of gravity decreases. And actually the dominant force in these outer regions in the atmosphere is the magnetic force. So these magnetic fields are sort of guiding these particles like beads on a string, or they're like surfers on waves. These surfers are the charged particles, which you're seeing in these images, but they're following magnetic field lines. So these loops that you're seeing are magnetic field line loops, and the particles are sort of riding along them. And brighter areas are hotter, darker areas are cooler. And you're seeing solar flares. There's a solar flare there, that big flash of light. It's like a paparazzi bulb going off with a coronal mass ejection following right along that solar flare. So if you're interested in watching these movies, just go on Google and search Solar Dynamics Observatory, and you can get these images are actually live. You can get them updated every single minute. So this is one tool that space weather scientists and space weather forecasters use to understand what's going on the solar surface, and to better understand what space weather might be coming at us as well. So, there's lots of energy on the sun, as we can see just from those movies. Where does this energy go? Well, it sort of streams along through the solar wind. These charged particles are sort of, part of the energy which comes off of the sun. And these charged particles in the solar wind bathe the entire solar system and the objects within it, in this soup of energy and charged particles and also magnetic fields. So when that soup kind of hits Earth, when that wind hits us, it doesn't just flow right down to our atmosphere. We actually have our own magnetic field, which generates a bubble around our planet, which we call the magnetosphere. So if you've ever taken a bar magnet, just a regular iron bar magnet, and you put it underneath a piece of paper and you sprinkle some iron filings on the top, I'm sure you've all done this in middle school or elementary school, you can actually see the magnetic field lines traced out as sort of what's called a dipole magnet. So you have field lines coming actually in Earth. They come out from the bottom, from the South Pole, they wrap around. So the magnetic field is pointed north in Earth's magnetic field, and then they come back down over the North Pole and into our North Pole. So, in a perfect world, this would be it'd be a perfect sphere, a perfect dipolar sphere. But since we have the solar wind pressure, it's just like a rock in a stream. You have water that's flowing around this rock, and in this case, the rock is the Earth, and the stream is the solar wind. And the magnetosphere sort of carves out this protective cavity through the solar wind. And that magnetosphere gets stretched and compressed at the day side and stretched out towards the night side, which forms the magnetotail. So the energy from the solar wind doesn't just bounce off our magnetic shield. Some of it does penetrate down into our magnetosphere, and it goes right over the poles. All those particles get funneled through various processes, sort of like a pinball machine. They get bounced around, but they eventually get funneled over our poles, sort of where the magnetic fields all converge. That's why we get auroras near the North and South poles, notably the North and South geomagnetic poles, not the geographic poles. And in our atmosphere, auroras are created in the ionosphere. So it's one of the highest layers in our atmosphere. You can see there on the right, the different layers. The troposphere is really what we're all in, essentially up to around 10 kilometers, where airplanes fly, is the troposphere. And that's where all weather on the ground takes place. So if you've ever, heard people say, well, it needs to be clear to see the aurora. Well, this is why. The aurora is taking place in regions up here, around 50 to 100 miles in altitude. Actually, it can actually go all the way up to 200 miles in some really, extreme cases where you get, a lot of tall pillars and things like that. Basically, clouds are all down here, the aurora's up here. So it needs to be clear to see the aurora. Makes sense. So, the gas that we breathe on the ground is nitrogen and oxygen, N2 and O2. As we go higher up in the atmosphere, there's less to really keep that air, bound to the ground. So it starts to sort of fizzle out. And actually those molecules, those N2 and O2, become O plus, so single oxygen, and N2 plus, which is ionized nitrogen. So these gas molecules break up into their own charged particles. So now we have charged particles coming down from outer space, remember, along those magnetic field lines, and they eventually hit our atmosphere, and these charged particles, these nitrogen and oxygen charged particles, and we get aurora from these reactions when these particles from outer space hit our own gas molecules and particles in the ionosphere. It's just like a neon lamp, except for the electricity is coming from outer space instead of from a wall outlet. And it energizes this gas and produces light in specific wavelengths. So we have nitrogen that glows red and blue. We have oxygen that glows red and green. And the different aurora shapes that you see in the sky are really due to different sort of rain cloud shapes, or these different shapes in the magnetosphere that are responsible for dumping the particles in. So I always like to use the analogy that if you've ever seen a puppet show, right, you can only see the puppets and maybe some of the strings that the puppets are attached to, but you never see the puppet master. It's the same thing as the aurora. The aurora in that case is the puppet. The magnetic field line is the string in which the puppet's attached to, and the puppet master is the magnetosphere. So really everything's being driven by the magnetosphere, but we're seeing it within the aurora. That's why scientists study the aurora, because from the different shapes and colors you see in the northern lights and the southern lights, you can infer different plasma processes and different scientific phenomena that are going on in outer space that you can't otherwise detect. So it's like a TV screen for the magnetosphere is what we like to say. So again, the aurora is like a giant neon lamp in the sky. So I just used ChatGPT and just made this image, which I thought was funny. So why do some places get aurora every single night? Well, I'm up here in Fairbanks, we get auroras all the time. Other places like Iceland or Tromso are similar, and it's because Fairbanks and Iceland and Tromso and other places are underneath one of the auroral ovals. So we have a northern auroral oval called the Aurora Borealis, and we have a southern auroral oval called the Aurora Australis. And these two auroral ovals are where you can see aurora every single night. It's clear and dark as long as you're underneath one of these ovals. And they're usually centered around 68 degrees geomagnetic north and south, roughly. The northern and southern geomagnetic poles are actually not directly in line with each other. So the northern geomagnetic pole, I don't know if you can actually see my webcam, but it might be up here, sort of above my head. Then the southern geomagnetic pole is a little bit offset. So, roughly 68 degrees geomagnetic north. But anyways, you want to travel to one of these locations underneath the auroral oval if you want to see the aurora consistently, which is why I live here in Fairbanks. It's a great place to go to school to study the aurora if you can see it every single night. But every single night, we see the aurora. We also see the aurora do some really interesting things. So over the course of the night, the aurora can sort of change, and sort of go through what's called a substorm cycle. So the aurora sort of charges up and explodes. And these explosions are called substorms. So the phases of substorms are sort of in four parts. You have the growth phase where you have thin auroral arcs. So let me see if I can pause this movie here. So when you have thin auroral arcs stretching from east to west. So, okay, well, that was the onset and the expansion. But you can see here some auroral arcs. This is an all-sky camera. And to your eyes, this might not look super impressive. Usually the growth phase is characterized by very faint aurora. So people think sometimes that the aurora is actually going away when it's really charging up. But here you see some growth phase arcs spanning from east to west. And then if I play the movie, you can see one of those arcs forms. It's very hard to catch because it only happens within a minute. Little beaded structures. That's actually what I'm studying for my thesis. These little auroral beads will form along one of the arcs. And then the aurora just opens up into the substorm expansion phase where it just goes crazy all across the sky. So you can see there. And now we're in a recovery phase where you have a lot of pulsating aurora. So this is when the aurora needs to kind of cool down and just kind of take a break. Usually you just have one substorm a night. So, these growth phase arcs start around 10 p.m. to 1 a.m. and then the onset happens right after. Expansion usually lasts for 15 to 30 minutes, and then recovery is usually basically the rest of the night. But in this case, we had some activity and we had a recovery phase, but it never really quite calmed down. You still can see those growth phase arcs, those east to west stretching bands. And then, okay, well, so I cut off the all sky video, but I was actually out this night and there was another substorm, but usually you just get one a night. So, but again, let's just play it back in so you can see. So this is the growth phase. And again, this is not the entire night. I've just kind of trimmed this one time lapse down so you can see just the expansion, but yeah, so you can kind of see these beads. This is after they've sort of evolved into curls, but this is a bead here. This is one here. This is another one, another one, another one. And then you have the expansion phase where the aurora just goes nuts. So that's the substorm sequence. And we usually get one of those a night. And you can see these substorms from lower latitudes too, like Michigan, for example. You're just going to see pillars dancing on the horizon most of the times. But if you're actually underneath the auroral oval, you'd see, a much more dynamic display filling the entire sky. But what causes, these really big nights of aurora? What causes these, big auroral substorms? So I didn't mention this, but not all substorms are created equal. You have some substorms that are relatively weak, and then you have some that are relatively strong. And you can get some really, really good nights of aurora. You can get some really bad nights of aurora, and you can also see the auroral ovals. And people in Michigan will know because this has happened a lot this year. But you can see the auroral ovals expanding towards the equator. And we saw that in May for sure when we had aurora seen all the way as far south in the northern hemisphere as the Yucatan Peninsula in Mexico, Morocco. I think even Oman saw it, which is in the Middle East. So what causes those big auroral storms, right? Well, the sun can get angry. And this is going back to space weather. So these gentle breezes of space weather can turn into giant storms. So coronal mass ejections are one such phenomenon that can create these big gusts of wind, I like to call them, or solar storms. CMEs are like sun burps or sneezes. They're big ejections of charged particles into interplanetary space. And these CMEs are basically bits of the sun's atmosphere that have been launched off from usually a solar flare or something. These CMEs can be directed at Earth like a cannon, swiveling on the sun, shooting out cannonballs. And they usually take around 1 to 3 days to reach us. When they do hit Earth, if they're directed and hit us, some of that energy from the solar wind, from this big gust of wind, could get, again, transferred down into Earth's magnetic field through our magnetosphere and then cause auroras. So basically, if you have this wind constantly hitting us and all of a sudden you just really slam it, you can get more particles being funneled in and more auroras as a result. And those auroral ovals then expand further towards the equator. So CMEs can create what we call geomagnetic storms. And this is a video of a CME taken by the LASCO instrument on SOHO. So you're seeing a coronagraph, which is an artificial eclipse blocking the very bright sun. So you can see all of the solar wind being scattered outside of the sun in its atmosphere. So can we predict these solar storms? Well, we can, but it's hard. Thankfully, space weather scientists are helping us. And I know if you're interested, check out the NOAA Space Weather Prediction Center. They release news articles all the time. And there's also experts on social media. I'm not technically an expert. I think to be an expert, you have to have a PhD, but Dr. Tamitha Scove, also known as a space weather woman, she's a great resource and one of my friends. So definitely check her out. She's really good at sort of translating these very sciencey, hard to understand bulletins that SWPC releases down to a level that everyone hopefully can process. Can we predict the aurora? Yes, we can, but again, it's also hard. It's a little bit easier, I would say, to predict the aurora than space weather. The problem is that space weather, we just don't have enough tools. We don't have enough spacecraft in space actually measuring these things to say anything definitive. Like when something happens on the sun, we see it, exploding off the sun, and then we have to figure out where it's going. And then we just have to wait until it hits us. And sometimes it never hits us. And sometimes something else hits us that we weren't expecting. And so we don't have anything in the middle to like say, okay, well, it is coming for sure. We're like, yep, just making sure it's like hit a, it's almost like you're going around like a checkpoint, and there's a checkpoint that's like, yep, CME still on its way. We don't have that. So, people liken the, sort of capability of our space weather forecast to what we had for terrestrial weather in the 1970s. So a lot is, just unknown, and that's because we just don't have the instruments to measure what's going on. But for the aurora, luckily, we have more stuff. We have webcams, we have ground magnetometers, we have spacecraft within Earth's magnetosphere. We also have all of the upstream monitors like ACE and Discover measuring solar wind, and also all the other suites of instruments that we use for space weather forecasting. So, auroras are still hard to forecast, but luckily we just have more tools that we can use. So, this is not an aurora forecasting talk. I have a blog article on that on my page, and my page is theauroraguy.com on the bottom here, which you can go check out if you want. But just want to say briefly something about the KP index, because I know all of you probably have heard about the KP index. Don't use it for aurora chasing in real time. It's just not worth it. It's basically like trying to predict the rainfall or the chance of rain for the entire planet over 3 hours, when all you want is whether it's going to rain in Antrim, Michigan in the next 15 minutes, right? Like, it's just not good for that. It's not good for very localized forecasts of aurora, which, the aurora occurs in this huge auroral oval around Earth, but it can have localized sort of brightenings, and these substorms happen on very short timescales. The KP is a 3-hour average of global geomagnetic activity. The substorm is just on the night side. It's only really a third of the globe. It's, not the entire globe, excuse me. So KP is just not a very good tool to be using in real time if you're trying to chase the aurora. It's very problematic. It's good for sort of general conditions. Like if it's a KP9, of course, it's going to be more active than a KP1. I mean, the chances of you seeing a KP1 aurora in Michigan are very low. The chances of you seeing a KP9 aurora in Michigan are very high. But you can't compare a KP9 to a KP8 to a KP7. Like, there's not as much use of doing that, because really everything comes down to the substorm. If you can catch a really good substorm, and the substorms don't correlate with KP at all, really, you can see a really good aurora if you can see a really good substorm. So just as an example, up in Fairbanks, I've been chasing under a KP8 and it was okay. It was fine, but substorms weren't that great. The Aurora wasn't that active, very colorful, really weird night, just really weird behavior of the Aurora. But other than that, nothing amazing. Whereas last year I had like one of the best auroral displays I've ever seen, KP2. So, I mean, underneath, like, when you're really underneath the auroral oval, it does not matter at all. Do not use the KP. It gets a little bit more relevant at mid latitudes, like for Michigan, but still the best resources to use are like webcams, social media, online sites like aurorasource.org, or even better, just going outside and looking, right? You wouldn't believe how many times I get people that say, oh, I don't know if it's out, and they're in Fairbanks and the Aurora is literally exploding above my head. And I'm like, just literally step outside. Like, it's not hard. So just try and, keep your guard up with the KP index. Webcams are my favorite resources. This is my favorite resource up in Fairbanks. It's this all sky camera that the GI, Geophysical Institute here at UAF runs. But I have an Aurora webcam page on my site, which you can check out. And I've compiled a list of all the, what I found, all the best Aurora webcams around the US and Canada. So really, if you want to know if the Aurora is out, just check these webcams. I mean, the webcams are not going to lie, right? And the Aurora is so big. If you see it in Minnesota, it's going to be seen in Michigan too, if it's the same latitude, right? So people don't realize that either, is that the Aurora is not just in Fairbanks. It's not just in Detroit, or it's not just in Lansing or something. If it's being seen in Lansing, it's going to be seen in Maine. It's going to be seen in Washington. Like, the Aurora is huge, right? It's this huge oval. So if the entire oval is energized, I mean, you're going to be seeing it everywhere along that latitude line. So just keep that in mind too. So in Fairbanks, this all sky camera is good for really the entire sort of interior of Alaska, and even Anchorage too. You just got to, realize that the further north you go, the more overhead the Aurora is going to appear. But you can take exactly what you're seeing here and just sort of shift it to the northern horizon a little bit more, and that's what you'll see. So some other Aurora chasing tools, just really rapid fire here. We have the Ovation Prime model. This takes the real-time solar wind values that you see outputted by Discover and ACE, and just turns them through a fancy math equation and gives you this model. The GOES magnetometers, my gold standard for just the one tool to pay attention to. Seriously, you should all learn how to use this. You're just looking for the spikes, basically, these spikes in the GOES mag, and that correlates to substorms. The Aurora Electrojet Index, if you're into just a single number to tell you how active something is, look at the AE index. Anything over 1,000 for 30 or more minutes will give you a good auroral display, pretty much. So this is just a very small sample of all the tools out there, but these are the most common. And I think all these have use too, unlike the KP, which I think is generally not useful. All these have inherent use. So if you can get used to one of these, that'll be good. Better yet is all of them. But if you can just get used to the Ovation Prime model, I mean, that'll work out the majority of times. The more red something is, the better, right? So this year, Aurora has been really strong, and that's because we're in solar maximum. So solar maximum is here to pump up those auroras, and we should be seeing the peak soon, sometime this year or next year. So we're really seeing the peak of solar activity now, but activity with the Aurora peaks actually a little bit after the peak of the maximum. So the Aurora should be good for the next couple of years. We don't have to worry about things turning off. I've seen, news articles like that too, is, oh, solar max is in 2024 and 2025, it's going to be completely over. No, that's not true. The sun does not just turn on and then turn off. It takes a full 11 years for this thing to go from the bottom to the top to the bottom again. So we have a number of good more years left in the tank for us for auroras. And even during solar minimum, the Aurora doesn't disappear, especially does not disappear in the auroral ovals. You might not get as many geomagnetic storms bringing auroras down to Michigan, but the Aurora is still there. It's just there's not as much active space weather to sort of power these things. So now's a really good time to be an Aurora chaser. But are you guys ready? Do you have what it takes to be an Aurora chaser? Well, all it takes really is patience and a love for the night sky, and everyone can be an Aurora chaser. So more specifically though, here are some tips for planning sort of a vacation to see the Aurora. I always think there's two camps, right? There's the camp that wants to see it from their backyard, which is like all the people in Michigan, anyone from their own backyard, I guess. But those people have to rely on space weather to sort of pump up the auroral ovals and have basically be able to view the aurora from, outside the oval, and then you can just go to the auroral oval if you want, which is the other method. Just plan a trip to Iceland or Norway for a couple of weeks, and you'll see it no matter what. So, what time of the year is best to plan a trip? Well, it needs to be dark and clear. Aurora season in Alaska is roughly from August 21st to April 21st. Equinox months are better for whatever reason. Actually, scientists don't know why. But there's more substorms during the equinox months and also the shoulder months around the equinox. So not just March to September, but October, August, February, and April are all good. And then if you're looking for the most contrast in the night sky, third quarter and new moon phases are best to see the most contrast in the aurora. The time of the night also matters. Auroras don't usually start appearing until 10 to 11 p.m. in Fairbanks. People get this wrong. They think, oh, I'm going to go to Alaska in let's say they're going to go to Alaska on the solstice, right? I get this all the time. People want to go to Alaska right on the solstice. It's the darkest time of the year. You're going to see the most auroras, right? No, auroras, unless there's some strong activity, will not come out until 10 to 11 p.m. And that's just how it goes. The auroral oval does not care about how much darkness there is. All it cares about is being on the night side of the planet, right? Those particles are coming in from the night side. For the magnetotail, they're charging up the auroral oval on the night side. So, at high latitudes, imagine during the winter solstice, the Earth is tilted away from the sun. And, it's dark all the time, but it's really not the nighttime. It could be dark at noon, but it's still noon. And you just don't get auroras in Alaska at noon. So, it still has to be nighttime hours to see the aurora, usually from 10 to 11 p.m. until 4 to 5 a.m. And then those substorms usually happen around 1 to 2 a.m. in Alaska, but in general, across the world, 10 p.m. to 2 a.m. is good. And at mid-latitude locations, for example, Michigan, you may have to wait for one of those substorms to actually see the aurora. So, of course, on a quiet night, you're not going to see the aurora because you're not underneath the auroral oval, but if you have a really strong substorm, even if it's a low KP number, like I said, KP is just not great. You might see a little bit of glow on the horizon, like a little red glow. Let me just take a break real quick. I'm going to take a sip of my water. So where in the world is best? Well, it's really good to travel to places underneath the auroral ovals. It's much easier to get to the northern auroral oval than the southern auroral oval. There's things like the Southern Ocean and Antarctica that are blocking your view of the southern lights. So I recommend all these locations on the screen. I won't belabor that point. In Michigan, of course, you're not underneath the auroral oval, but you have some good dark skies. So dark skies are necessary to see the aurora, especially at mid latitudes when you're looking towards the horizon. There's a lot more sort of haze and dust in the sky. And I just picked out some spots here that are, potentially good, like Copper Harbor, Torch Lake, Port Austin. Those are all sort of in that Bortle 1 to 4 range. Bortle is the name of somebody, obviously, but it sort of measures the quality of your night sky. So a lower number is better. Anywhere from 1 to 4 means your night sky is pretty pristine. There's not a lot of light pollution. 5 to 9 means that there's more light pollution. So you can see like Chicago, Detroit, Milwaukee, Green Bay, these big population centers are all Bortle 7 to 9, not great for aurora chasing. Of course, if it's strong enough, like in the May storm, you can see it right from town. I mean, I see it right from Fairbanks and it's a 9, but the auroras up here are also a little bit brighter than what you could get down in Michigan. But, when I was 4 years old, the Halloween storm, I saw it right from Maplewood, and that was at Bortle 7 or 8, I think. So, I mean, you can still see the auroras from town, but it really helps to be north of one of these big population centers. And also, don't go south of Detroit and try and look north, right? Don't go south of Lansing and try to look north, because you're going to be looking right back into the city you just drove away from. So people don't realize this either. Go north of wherever you are and try and get further north. I mean, you'll technically be closer to the aurora too, but try and not have any big population centers positioned right to your north. So I have some locations for Fairbanks in my ebook. And if you're also just wanting to learn more about aurora chasing, I have this free ebook on my website here, which you can check out. So what should you look for? Well, the aurora can look very different in the sky, from a dull gray glow on the northern horizon to dancing green waves all over the place. Here are just some examples, especially down in Michigan. You're going to see more of a green glow or a haze than, one of these huge cinnamon roll auroras, which I can see up in Fairbanks a lot. But with really big storms, you could easily get features like this down in mid latitudes. It's just pretty rare, but usually in Michigan, North Dakota, Minnesota, you're looking at sort of a glow towards the horizon, which you don't actually know is aurora or not. I've definitely been there in North Dakota where I'm like, I don't know if that's aurora. So I'll just take out my phone and take a picture. And, if it's green on the back of the camera, if it's green on the phone, well, then it is aurora, obviously. So here's just some examples. Mid-latitude aurora usually looks different than high-latitude aurora. You usually don't get those discrete arcs at mid-latitudes like you do at high-latitude. So the substorm cycle that you see and that I was describing with, sort of these east to west aligned arcs, very thin, then the beads, then it sort of opens up across the sky, expands to the north, expands poleward. You don't really get that at mid-latitudes. You kind of see everything stacked on top of each other to the pole, to the horizon, to the north, the northern hemisphere. So just keep that in mind. It's very rare that you're going to see aurora like this on the right down in Michigan. Also, the physics of it is just very different. These auroras at mid latitudes are mapping to different regions in space. So, and those regions have different properties than the regions connected to the auroral oval, for example. So, in some sense, it's almost physically impossible to get auroras like you do up in Alaska, down in places like North Dakota or Michigan. It just looks, it will always look a little bit more diffuse and sort of curtainy and not so discrete, and with such well-defined arcs. Although it can happen if the auroral ovals are expanded equatorward enough. So like we definitely saw that in May. I was seeing pictures of the aurora like this from Minnesota. So one reason why auroras look more red towards mid-latitude. So if it's a really dark night without a moon, you can usually see some little red glow off to the horizon, even under very quiet conditions. And that's because you're seeing the tops of the aurora, which are red from a distance, and the curvature of the Earth means that you cannot see the greens on the bottom of those reds. So just keep that in mind. If you only see red aurora, it's not that there's no green there, it's that you're only seeing the tops of the aurora that are just very far away over the horizon. So now let's get into some aurora photography. I've actually not been keeping track of the time, so I'm going to go kind of fast through this because I think I'm rambling a little bit, but I'll be available for questions afterwards, and my email's on the screen. Feel free to contact me at any point about anything after this talk. I'm here to help. So for smartphones, it's very simple. Use night mode if you have it. Hold the phone steady. Use a tripod if you can. For DSLR mirrorless cameras, really quick basic stuff here. Use a 5 to 10 second shutter speed. You don't want it too long to where you blur out the aurora, and you definitely don't want it too long where you create star trails, unless it's something that you want, and we'll get into that at the end of the talk. But your aperture should be your lowest f number, widest aperture setting. Your ISO should be 1600 to 6400. Just ballpark. This will really depend on your camera, how much light is available in your scene, how bright the aurora is, your lens, things like that. I've used ISO values as low as 600. I've used them as high as 20,000. So the ISO is not sensitivity. It's just sort of how bright you want your image to be. It's basically the same thing as using the exposure slider in Lightroom. So don't get too out of shape about the ISO. And of course, shoot manual mode if you can. Aperture priority actually works okay now. The meters and cameras are so advanced that it can pretty much sense how much light is in the scene, no matter how dark it is. So I actually shoot manual mode with auto ISO for all my time lapses, and I'm going to be getting into that. But most modern cameras past 2020, 2019 can do even program modes at night, which is pretty insane. But manual mode is always good if you're just beginning to sort of get your mind wrapped around how to adjust all these exposure values and sort of understand how everything works and pairs together. So auroras can be hard to photograph, especially if you compare it to Milky Way photography. So not to rain on the parade of any Milky Way photographers, but you never have to really adjust your shutter speed when you're doing Milky Way photography. You kind of figure out your 400 rule, and if you're 20 millimeter lens, okay, 400 divided by 20 is 20, so 20-second shutter speed. Okay, I got that down. Where's the Milky Way? Okay, let me bring out my app. Okay, it's over there. Align your camera, focus on the stars, and then you're good. You can kind of relax. With auroras, you cannot relax. I mean, you can, but really you have to be on your toes. So, the shutter speed needs to constantly stay at a value where you're not blurring out the aurora. You need to make sure that you're not overexposing if the aurora gets really, really bright. And yeah, you just got to be on your toes and really watch what the sky is doing, and also keep checking the back of your camera. So what you don't want is a situation on the right where I thought I was good, 1.6 seconds, f1.8. Okay, that's a really short shutter speed. Now I was also at ISO 640, which is a really low ISO. This Aurora was just so bright. I mean, this was the second best Aurora I've ever seen. Actually, March 5th, 2022 is when I took this photo. Insanely bright Aurora. It blew out my shot at these settings. So I was not ready for that. I thought I was comfortable. I thought I knew what I was doing. And then the Aurora said, we can get brighter. And it did. And it blew out my photo. So you don't necessarily want this to happen. You want to be able to capture what's really in that white, which is more green and even some pinks as well. So yeah, keep that in mind, is that the Aurora can get really, really bright, really, really fast, especially during these substorm expansion phases. Now let's talk about time lapse. And first of all, what is a time lapse? Well, a time lapse is taking photos at a specific interval and setting those images at a video frame rate to show the motion of the scene over long periods of time. So basically you take a video and then you speed it up, or you take a bunch of photos, and this is how we're going to do it, is take a bunch of photos and then in some sort of video editing software, piece those photos together at a frame rate, like 24 frames per second or 30 frames per second, common video frame rates that you'll find, if you take out your iPhone, you can see at the very top, it'll tell you, right? 4K 60. Oh, you can't see because I got the blur on. 4K 60, 4K resolution, 60 frames per second. So it's really a video. All a video is 60 images per second that are being taken and then automatically compiled into a video. All that happens automatically on the iPhone, but we can do the same thing manually if we take our own photos and then just speed them up. So, if you're taking a photo every 10 seconds and your intervals, 10 seconds or like 11 seconds to give your camera some processing time, well, that's one photo every 10 seconds, 24 frames per second. You're really speeding up the natural progression of time by a huge factor, right? Which is why in these time lapses here that I've shot of the Aurora, you can see the Aurora really whipping around. So you're seeing it faster than actually how it appeared. But, depending on the shutter speed, you can get different effects. Like I think here I'm using a 15 or 20 second shutter speed. So basically the scene's moving faster, the time is progressing faster. So you just watch the sunset tonight in about 10 seconds, and obviously it took a few hours. So this is one example, and then the Aurora was getting really, really good, and then I actually bumped down my shutter speed to 1.6 seconds. So now you're watching the Aurora actually only a few times faster than it really appeared. So this looks really fast, but the Aurora was also moving very, very quickly. So yeah, your shutter speed is used to sort of determine all these factors. Okay, there we go. All right. So is it worth the extra work? Because it is extra work. You have to shoot a lot of photos. I mean, that's really it, is that it's a storage, it's sort of a storage burden, is that you might have 1,000 images that you have to edit, right? And that could be tens of gigabytes, hundreds of gigabytes. I mean, if you have a little laptop with a terabyte hard drive, I mean, you could fill it up in a night. So is it worth all this extra? Is it worth all this extra effort, all this extra work? You also have to edit the photos. Takes time. It takes a lot of processing power. I mean, I built this beefy computer. It's like an $8,000 computer, and it still takes hours to edit a single sequence. Well, I think it really is, because you can show the evolution of the Aurora. You don't miss any of the action if your camera's running the whole time. So I think it's actually just a better way to shoot the Aurora. You can set up your camera in one spot. Now, granted, you're kind of fixed with the field of view you have, but if you're very clever and you say, okay, well, the substorm might be happening soon, I'm going to angle my camera this way or that way to capture it. If you capture the expansion of the substorm to the north in Alaska, you can kind of angle your camera east or west, and sort of, you can, kind of anticipate that to happen. But that's kind of advanced. And I can answer any questions related to that too, if needed. But, you can choose the best moment from hundreds or thousands of photos as well. Like if you're constantly shooting, maybe the Aurora is better in frame 662 versus 661, right? And you can have that sort of nuance. You don't have to worry, oh, I don't know if I caught that, because you definitely did if you're shooting a time lapse. And most of all, you can enjoy the Aurora without getting stressed out about your gear and really messing with things. My workflow now is I just go out to the field and I set up all my cameras. I have 3 cameras. I set them all up. I know what settings I have, what settings I need to have. And, I know more or less now what the Aurora is going to be doing. I can just look up at the sky and say, okay, well, we haven't had the substorm yet. It's still in growth phase. So I'm going to set up my camera looking east, this one looking west, and this one kind of looking, northish. and I'll anticipate this poleward expansion with the substorm, and I just let everything go. I take out my lawn chair and I sit down and I watch, and it's great. I mean, I don't have to touch my cameras because I know everything's set up and ready to go. So I think time lapses are great because you don't have to worry. You can just set it and forget it. And I think that's the beauty of it, is really kind of going back to the roots of why we all do aurora chasing, which is the beauty of the aurora, right? You don't want to be sitting there messing with your camera while the aurora is doing this amazing thing in the sky and you're missing it and you're, flailing around with your camera and all stressed out. So I think it definitely is worth the extra effort. So how to actually shoot an aurora time lapse is a little bit more involved than just a single shot. Obviously, there's images, there's more images being captured, but you also have a little bit more to think about. So first off, you want to underexpose a little bit. I'd say half a stop to one stop. That just anticipates any big brightenings in the aurora that could blow out your scene. Now, picking the right shutter speed is the main thing. First off, you want to figure out how long you want your final time lapse video to be. Let's say you want it to be 10 seconds. So at 24 frames per second, that's a standard, standard cinematic video frame rate. 24 times 10 is 240. So just some basic multiplication there. 240 being the number of photos you have to take. So, okay, you got 240 photos at 10 seconds. How long is that? Well, 240 photos times 10 seconds is 2,400 seconds of actual shooting. You usually want about a second in between your shots. So your shutter speed and your interval, you want your interval usually to be about a second longer than your shutter speed, just to give your camera enough time to write the image to your SD card. So let's just for simplicity's sake, because 2,400 is a nice number. 2,400 seconds divided by 60 seconds in the minute, that's 40 minutes. So now you've cemented yourself there for 40 minutes if you want to get a 10-second time lapse. So 10 seconds really translates to 40 minutes of real time, sort of real world time. So that brings you to the second question, is how long do you actually have, right? Do you have 40 minutes? Do you have 4 hours? Do you have 6 hours? Do you want to be out the entire night? Are you just on the side of the road and, you're kind of like off the interstate and you think you're going to get run over? You don't want to, be there for 40 minutes. Maybe you just want a quick 5-minute time lapse. So maybe you want your shutter speed then to be 1 second. And then, that's 10 times less time you actually have to be there. So that's 4 minutes, right? So all these things are factors to figuring out what shutter speed you want to use. Also, of course, the lower shutter speeds you use, the quicker shutter speeds mean less light entering your camera. So your images are going to be a bit noisier, but also means the aurora is a little bit sharper. So there's a bit of a trade-off there, a little bit of balancing act. So yeah, just a lot of things going on. If you can anticipate a substorm expansion, so if you can kind of read the aurora and know these patterns, you can set a slightly quicker shutter speed so that you can capture more of this expansion phase, which can be, just over the course of 15 minutes, right? This onset usually lasts 1 to 2 minutes. So having a shorter shutter speed is nice. You can actually get those beaded structures and it's not just lost in 1 or 2 frames. Shooting with your lowest F number, always do that. And auto ISO allows your camera to keep the aurora from blowing out if it gets too bright. Again, auto ISO relies on the meter of cameras. So actually, if you set your camera to auto mode, how does the camera know what settings to calculate? Well, it looks at a little light sensor and it picks up how much light's in your scene and does some fancy math behind the scenes. Well, modern cameras are pretty good these days and can actually do that with low light. So I've been running my cameras in auto ISO this whole time, and it's been working out. So here's my editing workflow. Not going to get into this because I have a whole guide on it. I have a little like Aurora time lapse 101 on my website, but basically, you have your shots on your camera, which you've recorded. You've taken those photos, put them into LR time lapse or Lightroom, and then you do some processing on those photos, and then you bring them into Adobe After Effects. And I use a neat video plugin just for some additional cleaning up to do. So this is sort of my workflow that I've been using for the past few years. It's the standard in sort of the professional scene as well. So yeah, LR time lapse is free for sequences up to 400 photos. Lightroom Classic is unfortunately not free, but I think most people here probably have Lightroom or something similar like Adobe Raw for Photoshop, for example, or there's Luminar, there's what are some other ones? Capture One, I think, is another software. Lightroom does require, or sorry, LR Timelapse does require Lightroom, however. So I just recommend people use Lightroom for that reason, is that a lot of these apps will link up to the Adobe suite really easily. So this is my workflow. If you have any questions on it, we can tackle those. Really quickly, I have a blog on this as well, which goes more into depth, but our cameras see a lot more than our eyes can with the Aurora. So, our cameras will see all the really faint greens and reds that are really there in the Aurora, but our eyes cannot, because our eyes are rods and cones, these photoreceptive cells, and our camera, is comprised of pixels on a sensor. So, rods and cones work a lot differently than pixels. Rods are what give us the low light vision that we have, plus, allow us to see in the dark. However, they only give us grayscale vision, so only black and white, and we don't get details with our rods. We get details with our cones, and we get colors with our cones, but our cones take a little bit of light to activate. So when the Aurora gets bright enough, that's why you can sometimes see colors, because it's activating your cones. Now, when there's a full moon in the sky, or a little bit of light pollution, or like a street lamp, it can actually have the same effect as a really bright Aurora. Your cones can become activated, and you can actually see colors in the Aurora. So I always tell people, if they're just up in Alaska to view the Aurora, come during a full moon phase, or a half moon, where you get a little bit of ambient light in the sky. You can activate your cones and actually see colors in the Aurora, which you wouldn't be able to see during a new moon. So really faint auroras, for example, under a full moon will actually be green, whereas under a new moon, you might be able to see the faint aurora a little bit better, but it'll be gray. So there's more to this story, however, on my website. And I'm definitely over time, so I'm just going to zip through this. But citizen science is one way where you can actually contribute your photos and do real science. So aurorasource.org is somewhere where you can basically make reports that you've seen the aurora and upload your photos for scientists to use them, of course, with the right privacy sort of restrictions and permissions. So these reports provide a real-time map of where the aurora is being seen. So when you click yes, I've seen the aurora, it goes on a map, which then aurora chasers can use to also see, whether or not people are seeing the aurora near them. And this is really good during geomagnetic storms, when the Ovation Prime model, which you can actually see plotted here in this red-green color scheme, is not very accurate. So during geomagnetic storms, the Ovation Prime model does not do very well. It just kind of falls off. And that's because it's just not made for these extreme events, these sort of edge cases, right? So in this case, this is the May event. You can see the model was only predicting auroras down to like Minnesota, but people were recording auroras all the way as south as Mexico. So Aurora Source is a great way to actually figure out where aurora is being seen on the ground. Tons more citizen science projects out there that you can contribute to as well. And you can also directly collaborate with scientists through submitting your images. So you can submit them to Aurora Source or Skyward, and those are sort of the two main platforms where you can upload your raw files or even edited files too. And if you've seen something weird in the Aurora, scientists want to see it. And that's one sort of frontier of auroral physics, is figuring out what causes these weird auroras, these weird aurora-like features and weird phenomena going on. So if you see something interesting, make a post, email a scientist, email me. I'll take a look for sure, and make sure that you get credit as well. So here are some recent Aurora citizen science discoveries. I'm just going to zip through these as well. Oops. So we have Steve, we have fragmented aurora-like emissions, we have Ragda, we have dunes. These are all phenomena. You may have heard of Steve, and maybe not the other ones, but these are all phenomena that have been discovered, or at least have brought renewed interest from aurora chasers and citizen scientists. So, you could be the person that names the next Steve, for example. If you see something weird in the aurora, and scientists and scientists and other people say, oh, what we're seeing is actually markedly different than what we've seen before, which is what happened with Steve. Let's name it something different. You could be the next namer of Steve. Maybe you'll call it John, or like Jimmy or something. I don't know. But they've been looking at the aurora and figuring out that we're really seeing some weird stuff. So aurora chasers are really pioneering the field of aurora science. It's just really inspiring. To me, kind of sitting in both sides of the room, right? I'm an aurora chaser, but I'm also a scientist in training, at least, and seeing the ways in which aurora chasers are interacting with my science community is just really, really cool. I mean, looking at scientists and seeing in conferences, presentations where, my friends' images are being featured, and they're on this, podium with the scientists and being, shared in this venue is just really, really cool. So if you're seeing something weird in the Aurora, don't just think it's, not worth saying anything about it, right? Submit to somewhere like Aurorasaurus, Skywarded, get people involved and tell people what you're seeing, because it really could lead to something major. So now last subject, and then I'll be in to answer questions. Star trail photography is a type of long exposure photography that captures the apparent motion of stars in the night sky. So I mentioned earlier, right, we want to avoid star trails. Well, what if we actually want to see the motion of the Earth and what that does to the stars in the sky? Well, we can just leave our shutter open for a long enough time, and we can get that. So there's really two main methods. Star trail photography is relatively simple, thankfully. As opposed to aurora photography, it's actually pretty straightforward. So there's really two methods here. There's sort of the one-shot method, which is you just take a normal astro photo, and then you calculate the equivalent exposure for a long shutter speed. So, right, in a normal astro photo, I'm talking about you use the 400 rule to figure out your shutter speed. So 400 divided by the 35 millimeter equivalent focal length of your lens. So 400 divided by 20 millimeters is 20 seconds. So let's say you have a 20 millimeter f 1.4 lens, and you're shooting the Milky Way or just the night sky in general. Let's say your ISO ends up being ISO 1000. Okay, 20 seconds. ISO 1000 f1.4. Let's say that you want to take a star trail photo and you want your shutter speed now to be 4 hours. So what you're going to do is you're going to say, okay, 20 seconds goes into 4 hours how many times, right? 20 seconds, 40 seconds. Okay, let's just make it 30 seconds because that's easier on the math. 30 seconds to a minute to 2 minutes, 2 minutes to 4 minutes, 4 minutes to 8 minutes, 8 minutes to 16 minutes, 16 minutes to 32 minutes, 32 minutes to 64, 64 to 128. So now we're at 2 hours, 128 to 256. Now we're at about 4 hours, 4 hours and 16 minutes, right? I just did 10 stops of exposure on my hand. So now we're basically taking our 30-second exposure and we're turning it to 4 hours. That's about a 10 stop increase in exposure. So if we did that without adjusting anything else, well, we just get a white image. Everything would be blown out. There'd be way too much light coming in. So we need to adjust in the other settings, in the other direction. So this is called equivalent exposures. And there's charts online where you can take your settings and you can just shift one setting over this way and shift the other setting over the other way. It's a really good way to sort of, nail down exactly what you need to get the same looking shot, but just with different settings. And this is something that all beginner photographers do. And, at some point, and maybe all of you are already, thinking about this in your head, but you can sort of just do the math like I just did and figure out, okay, that's 10 stops. And let's say I'm at ISO, I think I said ISO 1000. So let's say I want to decrease my ISO all the way to 100. That's my base ISO. So 1000 to 500, 500 to 250, 250 to 125. Let's say I have an extended ISO that goes on to 64. Okay, so that's 4 stops. So, okay, I'm at f1.4. Okay, so 4 stops. I still have 6 stops to go. So I'm at f1.4, f1.4 to f1. What is it? What's the next one? f2, f2 to f2.8, f2.8 to f4, f4 to f5.6, f5.6 to f8, and f8 to f11. So I think I did that right. So that's 6 stops. 6 plus 4 is 10. 10 minus 10 is 0. Should be the exact same exposure. So what I just turned my ISO 1000 30-second f1.4 exposure to 4 hours, ISO 64 f11. And those shots should look the exact same, except the stars are going to be trailed. So that's the one-shot method. And if you're really good at doing those equivalent exposures, then go for it. And if you're really good at not bumping your tripod and being patient and letting your camera do its thing, go for it. You need some kind of bulb mode or intervalometer that can do a 4-hour exposure. But I personally like to do the time lapse method because it's a lot simpler. Just take a normal time lapse, normal astro time lapse. So, in that example I just had 30 seconds, ISO 1000, f1.4, just do a time lapse. And normal astrophotography settings apply. Use something like the 400 rule to figure out your shutter speed. Take a time lapse, and then in software, what you'll do is you will basically use some sort of star trail software like Sequitur, Star Stacks. There's a Photoshop action for star trails, And there's also Deep Sky Stacker. You'll basically take your time lapse, upload all the files. And the problem with doing a time lapse that you don't get with the one shot method is in between each shot, technically there's a little bit of delay in your shutter, right? Your shutter, goes bum bum, and then there's a little bit of a delay. There's like a 1 second, usually maybe a half-second delay, even if your interval's at 0 seconds. So you'll get little gaps in the trails like this, which some people don't like. So personally, I don't think it really matters too much, but if you're very particular, you'll use one of these software tools, which will fill in those gaps for you. So personally, I like the time lapse method because you can also get a time lapse out of it. So you can get your star trails and you get a time lapse. You get 2 for 1. One shot is easy because you just plug it into your favorite raw processor and edit it like any other photo. But that's how to do star trails. I'm personally not, I don't do a lot of star trails because I'm usually not, I'm usually worried about the Aurora blowing out my photos. So I'm a little nervous that to set my exposure for a one shot star trail when the Aurora could get super bright and just blow everything out. So I'm usually doing a time lapse, and I occasionally like to do star trails, but they're super cool. I mean, you can see the motion of the Earth here, and you can see, I think this must be close to the equator because you can actually see the 2 celestial poles here. Yeah, so this must be close to the equator because you can see what's probably the northern celestial pole here. The star is kind of curving more towards the north and curving towards the south, towards the southern celestial pole. So it's pretty cool. So yeah, that's really all I have for you guys tonight. I'm probably right at about an hour, I think. Hopefully that was educational, and hopefully, I covered a lot of things. So hopefully you've definitely come across with some knowledge here. I'll be in the chat now following this presentation, and you can ask me questions. Of course, my email is Ledvina@alaska.edu. Also, it's Vincent@theauroraguy.com. I'm really good at checking email, really bad at checking Facebook. So if you send me a Facebook message, it's probably not going to get to me. I have over 100 that I have not gotten through yet, and most of those are from the May store. So please do not message me on Facebook because you will likely not get a response. But email me and I will respond to you for sure. Other than that, my social media handles are just at Vincent Ledvina. I'm also known as the Aurora Guy. Fun story behind that. I'm not going to get into it now, just for the sake of time, but it's a fun one. People gave me that name. I'm not that I'm not that self-righteous where I call myself the Aurora Guy just for fun. Although I do, but people gave me that name. So because I'm a crazy Aurora chaser, I guess. But anyways, more info at theauroraguy.com. And yeah, thank you for listening. And sorry again, I could not be there live to give this. I think it's better to, if I'm able to, basically take a break in between me talking and the questions as well, because then I can sort of come at it from a fresh perspective. So yeah, with that, thank you all for listening. And this will be on YouTube and will be available on demand after this workshop as well. So feel free to check it out and use it as a guide or a reference whenever you need. Thanks.